They're in Taiwan. I hope at this time they would be asleep. So our paper will be published in the Attia Memorial volume. Get to that. Oops. Oops. Oh dear. Done something wrong already. Okay. So this is the outline of material that I will cover. Background material, talk about the space of commuting elements in SU2, retractions, commuting pairs, moduli space of flat SU2 connections on a genus 2 manifold. So let's start with a compact two-dimensional orientable manifold, genus 2. In other words, it's double torus. If you puncture it, then the fundamental group is the free group on 4 generators. And we will actually, I'm getting ahead of myself, we will actually talk about not representations of this fundamental group into SU2, because that space is actually not a manifold for any obvious reason. That there's a complication there. Turns out that it is a manifold, but not in an obvious way. So it's simpler to consider the space where the commutator of these generators is sent not to the identity element, but to minus the identity element. And then take the quotient of that. And that is a smooth manifold. So and we're studying not hum pi g quotiented by g, but instead the space where the commutator is sent to minus the identity. And that is a smooth manifold. That was what I was, that comment from here, that space has been identified, studied by Dasal and Ramanan, and has been identified with the space of planes in the intersection of 2 quadrics in the Grassmannian. These should note that hum pi g is actually a Poisson manifold, and the quotient, in fact, in this case, it does turn the space hum pi, the space that we will study is in fact a smooth manifold, and it's symplectic. So the space we will mostly study is M is the space where the product of commutators is minus the identity quotiented by G, and that is a symplectic manifold. It's a generalization of the space of gauge equivalence classes of SUN connections on a punctured oriented 2 manifold, which was studied by Attia and Bott in their 1983 paper, Yang-Mills equations on Riemann surfaces. Attia and Bott found that these spaces were torsion-free, and Attia and Bott computed their Betty numbers. The ring structure of the cohomology for SU2 was discovered by Thaddeus using methods of mathematical physics and algebraic geometry. The ring structure for the more general case was that appears in a paper of myself with Francis Kirwan, 1998. Using equivariant cohomology. and what we call the residue theorem. My point here is that in the genus 2 case, for SU2, these results can be obtained by much simpler methods. And we're basically, our main tool is the Meyer-Vietoris sequence. We're able to recover Atiyah and Bott's result in this special case, and also Thaddeus's result. There are some new results that came out of this program. One is the cell decomposition and ring structure of the space of commuting two tuples of elements of SU2. This previously studied by myself together with Paul Seelig and Tom Baird, independently by Adem and Cohen. Also, the cohomology groups of the manifold M and the cohomology ring of its quotient, where you collapse the subspace where one of the elements at least is in the center of SU2. Center is plus or minus the identity. We also obtain a new calculation of the cohomology ring of the space A. This was the space where the result was known due to Atiyah and Bott for the group structure and due to Thaddeus for the ring structure. We also obtain transition functions for the principal SO3 bundle, which is M goes to A. So I'll stop there and ask, are there any questions to this point? Okay. Oops. So the space of commuting two tuples is just the preimage under the commutator map of the identity element, quotiented by G. The structure of this as a group was discovered by Adem and Cohen. And the cell decomposition of this space was worked out by myself and Tom Baird and Paul Seelig, and also independently by Michael Crabb. So we write elements of SU2 as quaternions in this way. So this matrix in SU2 is written as Z plus Wj, where Z and W are complex numbers. Let me denote by T the maximal torus of SU2. This is identified with the circle group U1. For an element in G, there is an element theta in the closed interval between 0 and pi, so that little g is conjugate to the complex number e to the I theta. This occurs if and only if the trace of G is twice the cosine of theta. So the group G is foliated by its conjugacy classes, which are parametrized by the value of the trace map. So G cross G is also foliated by level sets of the trace of the commutator map. I'll write those as W theta is just the set of G and theta, G and H, where their commutator is conjugate to e to the I theta. I will also introduce the notation X sub theta, which is the two tuples where the commutator is equal to e to the I theta. So Eckhart-Meinrich proved that X theta is isomorphic to SO3 or RP3, in other words. And we describe a T equivariant homeomorphism from X theta to RP3. where T acts on X theta by conjugation and acts on RP3 by left translation. We've given an explicit construction of this T equivariant homomorphism. So I'll write script I as the space of two tuples where the commutator is equal to the identity. Space of commuting two tuples in SU2. So this is the union of all the X thetas. And introduce the notation X subset, that just means where the subset X sub open interval from 0 to pi, that just means the commutator is equal to, it's all the X thetas except for the one where except for X pi. And we show that this space deformation retracts to X0, the space of commuting two tuples. This result follows from something that is stated in Milner's Morse theory book. Milner writes that if F is smooth and C is an isolated critical value of F, and F has no critical values in the open interval, then F inverse of C is a deformation retract of F inverse of the open interval. We apply this theorem to the trace map, which maps from X theta to R. The extreme value is the case of where the trace is equal to 2. In other words, theta is equal to 0. Instead of directly using Milner's theorem, we use the gradient flow for the trace function. So the flow lines for the gradient of the trace function are closed. And every point in X theta is the endpoint of a flow line starting in X of u for some u. We can't, however, get a closed form solution for the equation of the flow lines. We did find a different retraction that is explicit. This is written by studying the arc length of explicit trajectories of the flow. So are there any questions?
Lisa?
Yes. Yes?
Hi. Just a naive question. So will you show us this explicit construction, or is it?
The explicit, I didn't include it because it is quite cumbersome to write down. Our paper is posted on the archive.
Okay.
So I can tell you where to find it.
Mm-hmm. Okay. Yes.
But I didn't want to include it in a talk.
Okay. Thank you.
Okay. So together with Tom Baird and Paul Seelig, we gave the cohomology of a suspension of the space of commuting two tuples, showing that this suspension is equivalent to the suspension of this wedge sum of S3, two copies of S3, one copy of S2, and a suspension, double suspension of RP2. By Mayer-Vietoris, we're able to compute the cohomology of the space of commuting two tuples as a ring. Turns out that all the cup products are 0. This space was also studied by Trevor Bazette, who was a student of myself and Paul Seelig. He graduated in 2016, and he showed that the space of commuting two tuples is in fact homeotopically equivalent to this wedge sum, from which you can extract the integral cohomology.
So, sorry.
Question?
Yes. I have a somewhat naive question. Maybe I don't quite understand the space of tuples. How is it? But somewhere there is this class of the symplectic form, right?
Okay, so the space of commuting two tuples is in fact not a manifold. So that space does not have a symplectic form. Okay,
but then the moduli space.
I mean, other than this is a subspace of the. This is a subspace of M. So M is Poisson, and M quotiented by G is symplectic.
Okay. So,
M quotient by G has the symplectic form introduced by Atiyah and Bott, where you take the algebra valued flat connections and you take their wedge product and take the trace and integrate. That's basically how the symplectic form works.
But you're saying that
it just comes from the symplectic form on the space of all connections. These spaces are symplectic quotients of the infinite dimensional group, the gauge group acting on the space of all connections. And really the symplectic form comes from the space of all connections.
Okay, thank you.
Okay, so M is a 9-manifold, and A is a 6-manifold. Whoops. Good. Can you see the?
We see Atiyah's space on the screen.
Oh.
5.
Yes, I know, but are you?
We cannot see you writing or.
Right. So there's something wrong with the pointer. Anyway, should I? I don't understand what's wrong with this. Is it worth going to my desktop? Where I can't use the. Actually, why don't I just share screen again?
Yeah.
Okay.
That might solve it. Okay. Except I have to figure out how to stop sharing screen originally. Oh, that's easy. Okay.
Now we could see the pointer moving.
Yeah. Okay, try this again.
But that was the computer screen pointer. I think Lisa was referring to the iPad pointer.
Okay.
On the iPad.
Okay. All right, that's better. So this M is a 9-manifold. A is a 6-manifold because the action of SU2 via SO3 is a free action on A, so, on M. So your quotient is a smooth manifold. So in fact, in this case, Atiyah and Bott obtained the general result for all genus of these spaces of flat connections mod gauge cohomology groups. The genus 2 case was obtained by Newstead in 1966. So the Betty numbers, the cohomology groups, are question are as follows. In dimensions 0, in degrees 0, 2, 4, and 6, you just get Z, and in degree 3, you get Z4.
Jeremy, do you have a question?
Is there a question?
No.
Okay. So Newstead found the generators for SU2. Actually, for all G, not just genus 2. And Atiyah and Bott found them for SUN. I will introduce an additional notation. A theta is the set where the product of commutators is minus the identity, but the commutator of the first two elements is conjugate to e to the I theta. So A is foliated by these A thetas. They're just the level sets of the trace of the commutator of the first two elements, X and Y. And these can be written more simply in the case where theta is not equal to 0 or pi. So we can write A as the union of two copies, open interval from 0 to pi, and open interval starting not including 0 to pi. So we have a decomposition of this into two subsets which intersect in RP3 cross S2. And basically we use Meyer-Vietoris applied to this decomposition. Let me give you some background on intersection pairings. So the cohomology group of A is generated by one element in H4, one in H2, and 4 elements in H3. If you want to understand it as a ring, you need to know the relations. In other words, which polynomials in these generators are 0. Because the cohomology satisfies Poincare duality, understanding the relations is the same as understanding the intersection pairings. In other words, understanding the values of polynomials in these generators evaluated on the fundamental class. Through de Rham cohomology, these can be thought of as, the generators can be thought of as closed differential forms, and the operation of evaluating on the fundamental class can be thought of as integration. So in now specializing to the genus 2 case, we have 4 degree 3 generators, which are called B1, B2, B1 prime, B2 prime. And I will construct degree 6 classes gamma, which are just products of these two classes. The choice of how these classes are labeled is not arbitrary. It ultimately comes down to how elements of first homology intersect. First homology elements which are Poincare dual to these third cohomology classes. Note that in this situation, these classes that I wrote down are non-zero. All the other choices of products are 0. And that again has to do with which one cycles intersect in the two manifold. So one relation that was found by Michael Thaddeus, this is more general. This is for genus G. And the gammas could be defined more generally. And there's a relation that reduces the genus. So you have classes A and F and gamma. These classes evaluated on the fundamental class of AG are the same as the same classes evaluated on AG minus 1. A surface, the space corresponding to a surface of genus 1 less. So here M and N are non-negative integers, and AG is the space of conjugacy classes of representations of a genus G surface. So we're saying the degree 6 cohomology classes are Poincare dual to a codimension 6 submanifold of AG, which is isomorphic to AG minus 1.
One question, Lisa. Do you know
Yes.
how this last equality, how did he prove this?
Basically, this is described in Michael Thaddeus's paper. It's in Journal of Differential Geometry. Thaddeus. Oh, what do I have to do to write? I don't want it to be okay.
Don't worry, Lisa. Yeah, I'll find
it's in
this paper.
JDG in 1992. Basically his proof is topological. He explicitly constructs homology cycles which are Poincare dual to some of these classes, and shows what you have to do to get them to, under what circumstances they don't intersect.
Okay.
He gives a very explicit construction. It's quite right in the last section of this paper.
Thank you.
Can I also ask a question, please?
Yes.
Which of these classes and relations come from the classifying space? Maps from sigma to BSO3?
Oh, yeah. The A comes. Okay, so Gonzalo, it's Gonzalo's question. So yes. The question is which classes come from the classifying space. So what you're referring to is a construction. So the answer is the A comes. It's the A that comes from the. So the F is actually the Durham cohomology class of the symplectic form. It doesn't come from the classifying space, but the A does. The A does come from the classifying space of the group action.
Okay, thank you.
So I'll define. I don't think the screen share. I don't think
we can see you wrote at the.
Yes, I know, but I tried to. Okay, apparently I tried to change to the next page and it didn't go forward.
No, maybe try to do as you did before. Try to.
Okay. Right. Oh, I have to stop sharing and reshare. Share screen. Okay, better?
Great.
Good. So I'll define capital gamma, which it, whoops, that's not what I wanted. This is what I wanted. I see. Oh. Sorry about that. Okay, that's better. So big gamma is the sum of little gamma plus gamma prime. In our case, the space corresponds, what I was talking about before, the space where you reduce the genus by 1, original space had dimension 6, and the new space is a collection of points. So what you find is that the evaluation of on the fundamental class of big gamma is 4. Equivalently, there's a symmetry group that tells you that these two quantities, little gamma and little gamma prime, are equal. So that will tell you that each of them is 1. So talk a little bit about the Philander formula, which played an important role in Thaddeus's finding these formulas. This encodes the dimension of the space of holomorphic sections of powers of the prequantum line bundle. So via Grothendieck, Riemann, Roch, this is written in terms of the Chern character and the Todd class. So in terms of the generators I gave before, the first Chern class is just F, and as I said, this is the Durham cohomology representation of the symplectic form. So the Chern character is just X above F, and the Todd class is X above F multiplied by a polynomial. It's actually a polynomial in the class A. I write it as a rational expression in the class A, square root of A, but because these are even functions, it winds up being actually a polynomial in A. So that's what we're evaluating on. And this formula was first proved by Boville, Laszlo, Faltings, Kumar, Narasimhan, and Ramanathan, Sagie, Tsuchiya, Ueno, Yamada for SU2 connections on a surface of genus G. There are now more general proofs for more general groups, not just SUN. In our case, the formula winds up being this trigonometric expression. And this formula can be used as noted above to give formulas for the intersection pairings of in powers of A and F. So the way that works is for general G, the intersection pairings A to the M, F to the N, M and N are just non-negative integers, becomes this expression in terms of the Bernoulli numbers. So in the genus 2 case, it just becomes involves Bm minus 1. The only relevant values are m equals 0, m equals 1. So for m equals 0, we find the symplectic volume of A, which in this case is 4. For m equals 1, we find that the intersection pairing of A with F gives you also 4. In particular, it's not 0.
I'm sorry, Lisa, I'm just
Yeah.
a little confused. So how is it? You said before F was the symplectic
F is
form,
the symplectic,
right? It shouldn't be integral of F
Oh,
cubed.
yeah, sorry, that should be A squared. No, A is into, what's wrong here is the A cubed, because
Yeah.
A is a, yeah.
So it
So
should
that,
only be F.
no, sorry, that one should be F cubed.
Yeah, right.
Sorry, I used the wrong notation. Yeah, so this, sorry, F cubed. Yeah, thanks for spotting that. So AF is equal to the fundamental class, and F squared is 4 times A. So the 9 manifold, right, this is mu. Mu is the product of commutators map. So this is the, oops. This again. M is mu inverse of minus the identity. M theta, also the level set of the commutator map. And this is a restricting to removing the part where the commutator of the first 2 elements is -1, you get a trivial bundle. This means you actually get, restricting to each of these subspaces, removing 0 or removing pi, you get a trivial bundle. So you can have, you write the transition function for this. The bundle is trivialized if you remove only pi or only 0. So those subspaces, you get a transition function, which is just the map that sends G and H to G inverse H. I do use that. And let me define M caret, which is M quotient U, where U is the set where one of the elements is in the center of SU2. The cohomology groups of M check with mod 2 coefficients are equal to Z2 in all dimensions except 1 and 8, and equal to 0 in dimension 1 and 8. And with integer coefficients, we find Z in dimensions 0, 2, 7, and 9, Z4 in dimensions 4 and 6, and otherwise 0. And that really comes from that decomposition. I would like to note WALI'S theorem. Wald proved that if Y is a 6 manifold where all of the cohomology groups these are integer cohomology groups. All of them are Z in degrees 0, 2, 4, and 6, and some even power of Z in degree 3. In that situation, we'll prove that Y is the connected sum of some space Y prime with a number of copies of S3 cross S3. So this fits well with our result. In our case, we write A check as
Lisa, I think WAL here is for simply connected six manifold.
Lisa?
Oh, we lost Lisa. We lost Lisa.
I know. Hang on.
Okay, you are there.
Okay, you're back.
Okay. Share screen again.
There was a comment by Paul
Yes. Mm-hmm.
that I think that Paul, do you wanna make it?
Well, I was just saying that in WAL, Y should be a simply connected six manifold.
Oh, yeah. Sorry. Yeah.
Yeah.
Probably you can't see my screen.
No.
Okay, I'll try this again.
It says has started screen sharing, but
well, I have. Yeah, I know, but it has, AirPlay unable to connect to. Okay, so unable to connect to my computer. I don't know why.
Okay, try it again.
Yeah.
You could try it again, and if that doesn't work,
Yeah,
then perhaps you
then we go to the desktop. I'm nearly at the end, so
Okay.
this is the last section. Yeah, it's. I think we probably better go to my desktop. It's thinking, so.
Okay.
Right. Yeah. Maybe.
Okay, so I should stop share. Okay,
Yep.
so. Okay. Only now I can't. Now I don't have anything that I can press to. I don't have a screen share button.
Right, because you were logged out, so I need to make you a co-host again, I think.
Yeah.
Oh no, you are actually a co-host.
Right. So
let me try again.
Oh wait, let me try share screen.
Yeah.
Only. Okay, desktop. Can you see my screen? Or
Yes. Yeah, we can see it. Mm-hmm.
Okay. So
it could be with maybe.
Oh, I need to go to full screen.
Yes. Yeah. I think it would be worth doing it.
Yeah. Better?
Yes. Yeah. That looks perfect.
Okay. 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 So since we know the transition functions for the Meyer-Viator sequence, we can deduce that H2 of M prime is Z for Q equals 0, 2, 7, and 9. And yeah, sorry, that was, and for 4 and 6, you get Z for 7, Z mod for Z, and all other values are 0. Correspondingly, the ring structure is cohomology of A. So you have generators in degrees 2, 4, and 6. This is what I was calling F earlier, and this is what I was calling A earlier. And the relations are, as I said before. Z is the fundamental class. We can also find the ring structure of M prime, and then the cohomology of M is the direct sum of the cohomology of M prime with R, where R is 0 in degrees 0 and 9, Z4 in degree 6 and 3 and 6, and in degree 5, R is Z mod 2, direct sum of 4 copies of Z mod 2, and nothing in degree 1 and 8. So I will leave you with some references. This is Atiyah bought the paper that I mentioned by myself and Tom Baird and Paul Seelig, Crabbe's paper. This is the paper where our result will appear. The Atiyah memorial volume of the QJM. Finally, Narasimhan Seshadri's paper was fundamental to Atiyah and Bott's paper. And these were the papers of Newstead and Wall. This is the paper I mentioned of Thaddeus. And Edward Witten's paper was fundamental to finding the intersection pairings. And this was the main ingredient in my work with Francis Cohen. So I think I should stop there and take questions. Thank you.
Thanks a lot, Lisa. Let's first start thanking Lisa for her talk. Now it's time for questions. I see Anton wants to ask a question.
Okay. Can I get rid of the screen share, or
yeah,
maybe not?
Well, I don't know if somebody wants to refer.
Okay. I'll leave it.
To see the faces.
Yeah. Okay. Go ahead.
Less intimidating, so you can see.
Yeah. Go ahead.
Anton.
Oh, okay. So, Eva, so you're assigning questions just like that? Okay, sure.
I thought that you had a question. I'm sorry.
Oh, I mean, I will have questions certainly, but okay.
Okay.
Maybe, yeah. Sorry. Maybe just Lisa, to what extent those refined techniques that you described today, for instance, if you want to do like as you do for other genera, how would it work, right? Those ideas in particular where you introduce for each particular you control the conjugacy class of each particular commutator. So there were only 2 of them. So they belonged to some common conjugacy class. But if you have more of them, would it work? Those more complicated moduli spaces.
Okay, so for SU2 and higher genera, you would be able to carry out a similar program, but it would be quite cumbersome. And I'm not. Certainly, we have not tried to do this.
But you're saying basically it should work.
Well, I mean, you should be able to treat it by Meyer-Vietoris, but I think it would be difficult.
Mhm.
It would be complicated.
Okay.
So do these new proofs that you obtain of classical results can have other applications other than the ones that you have explained? It looks like they are like quite interesting new tools or new results. Did you think of other applications?
There would be other applications. We really got into this partly from starting from a project with Nanko and Eugene and one other collaborator. We were looking at the genus zero case.
Okay.
And where there, as I mentioned, there's no reason to expect that this should be actually smooth, but in fact it almost by a coincidence it is smooth, and it's actually isomorphic to CP3.
Okay.
But
yeah,
it's not clear that writing that space using level sets
mm-hmm.
doesn't lead naturally to the smooth structure, to the conclusion that this space would be smooth.
Okay.
And in fact that paper we were tantalized by the fact that there is a natural way to relate this object to some space that has a torus action where the dimension of the torus is half the dimension of the manifold.
Okay.
And the action is Hamiltonian, and the moment and the image of the moment map is only defined on an open dense set, but its image, the closure of its image, is a tetrahedron. So what you're getting is something that looks like the moment polytope for CP3. We were trying to rediscover the fact that it was rediscover the identification of this with CP3, but that was how we got involved in this project.
Oh, okay.
But
okay.
We were unable to complete that project.
Okay, and then
well, I mean
okay. Yes.
As far as we got, we were able to identify the open cell and the faces of the moment polytope. We weren't able to identify the edges and the vertices.
Okay.
Let me add something. After the fact, given the answer here, you could use Meyer-Vietoris to work backwards and find that the cohomology of the inverse image of the identity is in fact the same as the cohomology of CP3, and that would get you at least at their homotopy equivalent. But that's kind of backwards. I mean, so you could work backwards and deduce that from this.
Well,
so yes, there are generalizations to higher genera and other groups. Not just, I mean, we haven't tried thinking about SU3, for example. SU3 would be quite a lot more difficult than SU2.
Maybe some naive questions. So your techniques allow to do basically everything of a Z. I even don't quite know, like in the general case, is everything over Z known? Like for, as you say, for higher genera or for higher rank?
So Atiyah-Bott's result is over Z, and that is known for all genera and for SUN.
Okay.
Okay.
And that came out to be torsion free.
Yes. Well, Atiyah-Bott proved that space was those spaces were always torsion free.
I was looking at YouTube, asking if there are questions. You have 3 people thumbs up to your talk, so they liked it. At least 3 people did the thumbs up. No questions in YouTube. So do we have questions here? Other questions, comments, suggestions?
Suggestions: learn to use my iPad.
So the other,
I have to by next term because I'll be teaching using it.
Okay, you get.
I've been on sabbatical, so I've been sheltered.
You have been, yeah. You could escape from this teaching online. Now the second semester you cannot escape. Yeah, it's quite a thing. Then you'll go.
Well, I mean, this semester I've been watching a lot of Zoom talks, but just not teaching.
Yeah, it's tricky. So, I find it tricky to change from iPad to and then you don't see the faces, and it gets a while to get used to this. So Lisa, thanks a lot for your talk, and it was very inspiring. Now we will look at these new proofs in your paper, and the other paper, the other collaboration you were mentioning. I understand that it's ready and we can find.
No. The other collaboration, that paper is published. It's in. Did I reference it here? It's in Geometry Dedicata, 2017.
Okay, perfect.
I think it's the Bill Goldman's birthday volume.
Okay, it's nice that you can.
Anyway, that's all of this is on archive, but that's published.
Very refreshing to see that we can use the Maya reactors to find nice proofs of things. So we will all look at this. So thanks for your very nice talk, and I wish you the best, and all the speakers, all the people in the audience. And next week we still have another talk in the seminar. This never stops. We have a seminar by Marius Kreinik, who is around, but he didn't reveal the content of his talk.
So I actually have the title now.
You have you are the only one.
Maybe, perhaps. So the title is From Poisson Geometry to Almost Geometric Structures.
Wow. So we cannot miss that talk. And this will be before Christmas, and then we have Christmas, okay? And we have a period without talks. So let's thank Lisa again for her very nice talk.
Thank you.
Thank you very much.
Thank you, Lisa. And we'll see you all here next Thursday, and then we will all go on vacations for some days.
Okay.
Thank you.
Thank you, everyone. Thanks so much.
Good to see everyone.
Thanks, Lisa, for the talk.
Bye-bye.